This is the brief on geometric scaling of the metric cross product. So the source material tackles a really core mathematical challenge. What happens if you stretch your coordinate system? Like, let's say you just double the z-axis. How do you make sure a fundamental operation, like the cross product, still gives you the right answer, geometrically speaking, in that new kind of warped space? Okay, first up, the key to accuracy is figuring out the metric determinant. Think of it as this one number that quantifies exactly how much your coordinate system has been stretched. It's the essential scaling factor that you're going to need. Second, we use that number to properly scale the calculation itself. The cross product relies on a tool called the Levi-Civita tensor density. And in that example where we doubled the axis, the sources show the scaling factor is, well, it's exactly 2. This means that tool has to be adjusted to be twice its standard size. And finally, this step is absolutely non-negotiable for making sure everything is geometrically correct. The visualization in the sources makes it super clear. The correct scaled cross product, that's the red vector, is visibly twice the magnitude of the standard unscaled one. It's proof that we've successfully accounted for the distortion in the new system. Incorporating the metric determinant is truly the only way to guarantee your vector operations stay accurate after a coordinate transformation.